In physics, there are examples where particle or body changes its position with time. And when we study this change in position with time, we come across certain terms like velocity, acceleration, and we will discuss that how this velocity, acceleration with respect to time, these graphs, how does they look. Now to begin with, I'll start with distance and displacement. Now distance is the length of path traversed by a body, and displacement is the distance between the original and the final position. So in this example, here the distance covered is total distance to and fro is total distance 10 meter. But in this case, if this person comes back or returns to the starting position, then the displacement will be 0. I will give you another example where a particle changes its position with time, and the change of position, the value of the change in position remains same for every time. That means for every second the particle is traversing the same distance or displacement or position. Now from this we can draw a graph between position and time where the graph shows a linear straight line. But from this graph we can also infer the velocity and the acceleration of this particle, and we know that velocity from the position can be defined as rate of change of position, and from the velocity we can also define that acceleration is equal to rate of change of velocity. So in this example, here the position change remains same with every time, so velocity remains constant and there is no acceleration, so there is no change in velocity whether increasing or decreasing, therefore acceleration becomes 0. Now I'll give you another example where the red car and the blue car. Here the red car crosses the blue car from at 7 seconds, which means that these two bodies or cars, they are traversing with different velocity, and from this position time graph we can infer about the velocity of these two cars as well as the acceleration. So there will be a lot of examples in physics where the change in position, from the change in position time graph we can infer or conclude or get some information about the velocity and the acceleration of that body or particle. In this, where if the body or the particle is at rest, then the graph between x and t will be a saturated or straight line parallel to x-axis. Similarly, for uniform motion, that means the particle is traversing or covering equal distance in equal interval of time, then we say it's a uniform motion where the slope of this graph will give me the velocity. Similarly, there will be another graph which is called the non-uniform motion, where the position and the time, the change in position and time is not uniform or not linear. So from this non-linear graph where the position and time is not uniform, then if that happens, then how do you conclude the velocity? So when you have a positive value of the slope from this graph, then that represents that particle is moving in the positive x direction. But when you have a slope which is greater than the previous one, like here in this case the slope of b is greater than a, which means that the particle in this position is covering or moving faster than it was at a. Similarly, if you have the particle at this position c, here the slope is 0, which means that the particle is instantly at rest, so there is no velocity. So from this graph, or from a nonlinear position time graph, we can conclude from the slope about the velocity. Now what about the velocity time graph? So from the position time graph we can also conclude about the velocity time graph, or we can take an example from a velocity and time information and draw a graph from a velocity time graph. And from the velocity time graph, the slope of the velocity time graph will give me the acceleration. And if you want to calculate that for a body, which is how much distance it is covering, or the net displacement, you have to calculate the area under the graph. Now, if the velocity time graph, if it is taking the path ACB, that means the velocity is increasing, so acceleration we say as a positive acceleration, or acceleration increases. But if it traverses a path like ACD, then velocity is decreasing with time, which means that acceleration from this graph, the acceleration will decrease or return, and this both can be calculated from the slope. So if we want to calculate with the previous slides, then we can say that from a position time graph, the slope gives the velocity. A velocity time graph, the slope will give acceleration. The area under the velocity time graph will give us displacement, and area under the acceleration time graph will give us velocity. Now we will take some examples taking into consideration displacement, velocity and acceleration. Here, when the particle is at rest, then you will find that the position and time graph, it is on the x-axis. And because the particle is at rest, there is no change of position with time, so velocity will also be zero, and also acceleration, because acceleration is the rate of change of velocity. So if I take an example with a motion or a particle moving with constant velocity, then the graph between velocity and time will be parallel to x-axis, and because there is no change in velocity with time, so acceleration will be zero, and the velocity, the position time graph, it will be a linear. If I consider a particle or a motion with constant acceleration, that means acceleration, when it is constant acceleration, then the acceleration will be parallel to the x-axis, where x-axis is your time, and the velocity, because it is increasing with time, so velocity is increasing with time, that means acceleration will remain constant. And this velocity is changing with time uniformly at the same rate, so acceleration is parallel and constant, parallel to x-axis and constant. So if I have a motion with constant deceleration, then the velocity curve for this will decrease. So with time the velocity will decrease, and the acceleration time graph will be in the negative y-axis, parallel to the x-axis. So we'll take from the previous graph conclusions. We can take a few examples. For example, if you look into this graph, they are asking you, from a velocity time graph, they are asking you to calculate the acceleration for every path or from every time interval, and they are asking you what is the total displacement of this journey. So if I want to calculate the distance or the journey from O to OA, then acceleration is the slope. So you can calculate the slope in this region, and you get 2 meters per second square. And for the journey A to B, because it is parallel to x-axis, which means the slope is 0, so acceleration is 0. And from B to C, velocity is decreasing, so if you calculate the slope in this way, then you get the acceleration as retardation or negative acceleration. So for this problem, if you want to calculate the displacement covered by this journey, then you have to calculate the area under this graph, and this graph looks like a trapezium. So if you want to calculate the displacement, you have to calculate the area, half into sum of the parallel sides into the distance between the parallel sides, and you calculate, you get 96 meters. So if I want to calculate, infer about this problem or draw a conclusion, then we say that this body accelerates uniformly for first 4 seconds, then accelerates, that means velocity changes, and then moves uniformly for 6 seconds, and then returns, that means velocity decreases for the next 8 seconds. So we come to the end of this lecture.